Momentum carts are useful for observing both elastic and inelastic collisions. In order to model an elastic collision, which side of the cart should you turn inwards? It's going to be the magnetic side. And the reason is it's going to give you a softer area that allows you to bounce off, where the Velcro side is going to cause you to stick together, and that will reduce your kinetic energy. We need to conserve the kinetic energy if we want an elastic collision. It tells us to go ahead and gently push the carts together towards each other. Push the carts towards each other and model an elastic collision. If the total kinetic energy of the system is 100 joules before the collision, what's the total kinetic energy of the system afterwards? Well, it's an elastic collision, so energy is conserved. If it's 100 joules before, it's 100 joules after. We have a conservation of energy. With our real-life model, is kinetic energy truly 100% conserved? No, absolutely not. In real life, in our lab, we have loss of energy to friction, there's air resistance, there's noise or sound, there's places where energy is being lost to, as far as kinetic energy is being lost to. So we have a new diagram. And a little hybrid car, 100 kilograms is the green one on the left, is driving on a road at 20 meters per second. A big SUV, the pink one on the right, is 2,500 kilograms, moving 30 meters per second in the same direction. Bumps into it. Which direction are both cars moving after the collision? They're going to be moving to the left. There's no reason to imagine that that small car is going to make the SUV bounce off and go the other direction. The collision occurs in an experimental setting, and kinetic energy loss is essentially zero. In the collision, the hybrid has a velocity of 34.3 meters per second to the left afterwards. How fast is the van traveling after the collision? Here we're going to set this up where we've got conservation of momentum. Momentum is mass times velocity. So we're going to look at our momentum before and set that equal to the momentum after the collision. The momentum before is the momentum of the separate objects, mass times velocity, 1,000 times 20, plus 2,500 times 30. I made both of those velocities positive because everything's moving to the left, so this problem will be positive to the left. You can do negative, totally fine. After the collision, we've got 1,000 kilogram car moving at 34.3 from the problem, plus 2,500 times v, because we don't know how fast the van is moving. Once we put this together, we're going to multiply and add what we have on the left, and then divide over that 1,000 times 34.3, and we find that the van has slowed down to 24.28 meters per second. That's the final velocity of the van. What is the impulse felt by each car? Impulse is force times time. It's also mass times the change in velocity. We don't have force times time, so we'll do mass times change in velocity. We anticipate that they'll have the same magnitude but opposite in directions. The car's mass of 1,000 times final velocity, 34.3, given to us in B, minus 20, which is the initial given to us in the original problem. And then for the SUV, we have a mass of 2,500 kilograms times final velocity we calculated at 24.28, minus the initial velocity of 30. We'll subtract those velocities and then multiply by the mass and see that we get the same magnitude but opposite directions. Here we get 14,300 Newton seconds. You could have also used the units of kilograms meters per second. They are equivalent. When looking at impulse, we generally use Newton seconds just to keep impulse and momentum separate. And SUV was negative. And it's negative because it slowed down. If you used negatives to begin with, they were moving in a negative direction, your signs would be opposite of mine. If the impact occurred in 0.2 seconds, how much force was being used? Okay, well, we know impulse is force times time. We know our impulse was 14,300 is equal to force times the time of 0.02. Divide that 0.02 over, and we get the force in newtons, in this case 71,500. Draw a free body diagram showing the forces acting on the hybrid. Don't forget, this is near Earth. You've got force of gravity down. It's on a surface, the ground, so force normal up. and the car was pushed to the left from the SUV behind it. So we'll do an arrow to the left, and I'll just call it force applied. You could call it force from the SUV, whatever you like, as long as we understand that that's the direction of that force. Which car experienced a greater acceleration? Newton's second law tells us that acceleration is force divided by mass. If force is held constant, which it is in this case, acceleration and mass are inversely related. A larger mass will have less of a change in velocity. Change in velocity is acceleration. And here we're looking for something that has the greatest acceleration. The greatest acceleration will come from the smallest mass. The smallest mass has the greatest acceleration or change in velocity, and that smallest mass is the car. Superdude is flying in the air. He sees a bus flying wildly through the air. Oh no, he says, I will save them. The bus is 3 times more massive than Superdude. So if Superdude has a mass of m, the bus then would have a mass of 3m. Using the Velcro side of the momentum cards, try this model. Okay, that's if you're in the lab. Right before the collision, the bus has a velocity of 130 meters per second. So its V naught, its initial velocity is 130 meters per second. Superdude was simply floating in the air with his arms wide, so we're going to say his initial velocity was 0. What would be the velocity of Superdude bus system after the collision in terms of m, the mass of Superdude? Here we're just going to set up an inelastic collision, so we can have the mass of the bus times the velocity of the bus, 3m times 130, and we're going to add to that the momentum of Superdude, m mass times 0 velocity, and that's equal to the combined masses, 3m plus m, times what their velocity is going to be, and we'll call it v because we don't know. 3m times 130 would be 390m. 0 times m is 0, so we'll leave that alone. 3m plus m is 4m times v. From here, it looks like I can cancel the m's and then divide both sides by 4. When I do that, I'll get an actual numeric number for velocity. I'm not sure why the question said to do it in terms of m, because m does cancel out. We can actually solve this and get 97.5 meters per second is the velocity. We can go ahead and accept that as the answer. So I'm going to scratch out in terms of m. How many times faster than the bus, how much faster does Superdude need to fly upwards in order to completely stop the bus during the collision? So we're going to say 3m times 130 plus m times 0, or m times v, because now we have a new velocity, what we're trying to solve for, the initial velocity of Superdude. And that's going to be equal to 3m plus m, the combined mass, times 0, because they're going to be stopped after that collision. 3m times 130 is still 390m, plus m times v is equal to 0, so let's just add that m times v to, or subtract that m times v to the other side. So we'd have negative mv on the right. We can cancel out the m's again, and then we can just divide both sides by -1, and we get negative 390 meters per second for the velocity. A student says the longer it takes Superdude to slow down the bus, the better for the people on the bus. Do you agree? And yes, absolutely. We know the impulse is already set. The impulse is taking the bus from some velocity to 0 in this case. And so if we increase time, we will decrease the force. Time and force are inversely proportional because impulse is force times time. This is kind of like why we have airbags in cars, because an airbag extends the time for the collision to occur or for the car to come to a stop, and by increasing the time, that force is decreased. If the bus weighs 50,000 newtons and was traveling 130 meters per second at the time of the collision, how much work would Superdude need to do in order to completely stop it? Well, if the weight is 50,000 newtons, the mass is 5,000 kilograms, just divide by 10, and then the initial velocity is 130 meters per second. We know work is a change of energy. In this case, it's a change of kinetic energy. So if we solved how much initial kinetic energy we had, K naught, which is calculated as 1/2 mv squared, we would know how much kinetic energy is lost. And that would be the work, that would be the change of energy. So 1/2 times the mass, 5,000, times the initial velocity, 130 squared. We take half of 5,000, 2,500, multiply that by 130 squared. Let's get that in a calculator and get a value. We get that initial kinetic energy being 42,250,000 joules. That's how much kinetic energy the bus had, and it's going to come to a stop, so it's going to lose all of that kinetic energy. That is the change of energy, so the work is negative 42,250,000 joules. We know this because that's the initial kinetic energy, and the final kinetic energy is 0 joules, so the change is that subtracted. If it takes SuperDude 5 seconds to stop the bus, using your answer from D, calculate SuperDude's power output during the collision. If we remember, power is simply work divided by time. And if work is negative 42,250,000, and we divide that by 5, that will get us our power. So we just need to put this into a calculator and divide. And when we get that, our units for power is watts. Looks like we have 8,450,000 watts.